This is problem 50 from electromagnetic waves. Two glass plates and a wire form the system shown at right. The plates are 120 millimeters long. They touch at the left end. They are separated by a wire of unknown diameter at the right end. A broad beam of wavelength 680 nanometer light is sent directly downward through the top plate. The 17th dark fringe means destructive, of the reflection interference pattern occurs directly above the midpoint of the plate. What is the wire's diameter? So we have a wavelength of 680 nanometers, and we have glass, and air. The index of refraction for glass is greater than the index of refraction for air. The index of refraction for air is pretty much 1, and 1 is the smallest index of refraction that you can have. Dark fringe means destructive interference, but before I can figure out what formula that is, I need to know whether or not there is a phase shift. We are looking at the reflection interference pattern, so that's what you get for the wave that reflects here and the one that goes down here and reflects. Remember that these waves are actually traveling straight down and straight up, but if I draw them that way, you can't see what's going on. So we put a little bit of angle in there just so we can see what's happening. Okay, so this reflection here is off of air, which has a lower index of refraction. If we're reflecting off a lower index of refraction, there's no phase shift, so that's 0. This reflection is off a higher index of refraction, so that's pi, so there is an overall phase shift. Because this wave flipped and this wave did not flip. So now they are out of phase. So we're looking for destructive interference when the waves are out of phase. So 2d is equal to m times the wavelength. Oh, well, it's the wavelength in the material where the path length difference is taking place. The path length difference is taking place in air, so that's just the wavelength in air. So we don't really need to write material because it's the same wavelength that we have up here. Okay, now when m is equal to 0, d is equal to 0, and this is the first dark fringe. So when m is equal to 0, if you get the first dark fringe, and we're looking for the 17th dark fringe, then m is going to be equal to 16. Okay, now first we're going to find 2d and then we're going to worry about the wire's diameter. So this is the formula that I use. So I have 2d is equal to m is equal to 16, and the wavelength is 680 nanometers. So d is equal to 8 times 680 nanometers. And that gives me 5,440 nanometers. Okay, now I have to do a little bit of geometry to figure out what the diameter of the wire is. It's kind of unfortunate that we already used d for the path, not the path length difference. 2d was the path length difference, but in any case, we already used d, which is what I would ordinarily call the diameter of the wire. So I don't know what I'm going to do for that, but we're looking for this distance here. And we have the 17th dark fringe occurs directly above the midpoint of the plate. The plates are 120 millimeters long. So if we're looking at the midpoint, half of 120 millimeters would be 60 millimeters. This distance from here to here is the 5,440 nanometers that we found. And so if this occurs halfway along, then this distance here is just going to be twice 5,440 nanometers, which is 10,900 nanometers. So rather than writing that in nanometers, let's move the decimal place over 3 spots and write it in micrometers, which is times 10 to the negative 6th. So this is 10.9 micrometers. And if I write it this way, then I don't have to worry about what letter I'm going to use for the diameter of the wire. So that is the answer for problem 50.